Okay, so good morning, everyone. Let's get started. Please make sure you mute yourself during the webinar. I'm going to share my presentation. My name is Begoña Casas. I'm researcher in the Metallic and Ceramic Materials Unit of EURECAD. EURECAD coordinates the European project ToughSteel, that is about the fracture toughness as a tool to address cracking problems in forming and in service performance of advanced high-strength steel. This webinar has been organized in the frame of this ToughSteel project. Firstly, I'm going to give a very brief introduction to the ToughSteel project, and then we will have four technical speeches, one about fracture toughness to predict cracking resistance that will be given by David Frometa, a second one about the application of fracture toughness measurements in the industry, successful case studies that will be given by Michele Maria Tedesco. Then limitations on short edge formability simulations that will be given by Ole Sandin. And finally, the application of the essential work of fracture in sheet metal forming simulation by Ricardo Hernandez. If you have any questions, and finally, we will have some time for open discussions. So if you have any question, please feel free to type them into the chat box, and we'll deal with them in this part of the open discussion. I will start with a brief presentation of the ToughSteel project. This is a European project funded by the Research Fund for Gold and Steel, with the objective to promoting the fracture toughness as a material property to rationalize the crack-related problems in advanced high-strength steel. The project has a duration of 2 years. The consortium consists of 8 partners from four different European countries. Please please make sure you mute yourself. Can you mute yourself? Oh, thank you. Okay, the consortium consists of 8 partners from 4 different European countries, 2 universities, Louvain University, Luleå University of Technology, 1 research institution, that's EURECAD, this is the coordinator of this project, 1 end user, CRF, 3 steel associations, UNESID, Ger Contoret, the Associazione Italiana di Metallurgia, and 1 standardization body, UNE. As you well know, advanced high-strength steels comprise a wide range of complex multi-phase microstructures that show very high strength, relatively good formability, and excellent crash performance, which make them especially suitable for the structural and safety-related out-body components. Contributes to reduce the vehicle mass and improve the safety of the occupant. So in the last decades, a large number of advanced high-strength grades has been developed. But the rapid implementation of these materials in automotive has introduced new problems that are still not completely solved because of the limited ductility or formability of these advanced high-strength steels that compared to conventional mild steels that can produce crack-related issues that cannot be rationalized and predicted in the product design stage by the traditional approaches as the tensile test, for example, of the 4-minute limit curve. And this hampers the use of the advanced high-strength steels and the development of high-performance parts of reduced cost using these materials. That's why this project, the ToughSteel project, aims to disseminate to the main actors of the sheet metal forming community the possibility of measuring the fracture toughness by the use of the methodologies that has been developed in previous projects, the possibility of measuring the fracture toughness in thin sheets and use this fracture toughness to effectively address and solve crack-related phenomena as edge cracking, for example, and also to select and develop advanced high-stress materials with optimized scratch performance. The project will contribute to improve the efficiency and the competitiveness of the sheet metal forming processes involving high-strength steels. In the fracture mechanics, the fracture toughness is defined as the energy spent in the creation of two surfaces at the crack tip that give rise to crack propagation. The standard methods or the standard tests to measure this fracture toughness are complex and involve also exhaustive specimen preparation, and its application in thin schist is often difficult. So as a consequence, the fracture toughness of advanced high-strength steel are not applied the different steel makers, part makers, or the OEMs to the design of structural and safety-related components in automotive. Thus, its alternative is needed, an alternative, simple and faster experimental approach to satisfy the growing need of knowing the fracture properties of thin metallic cheese. And this approach has the essential workout fracture methodology has been developed in previous projects. And the valorization and dissemination of these new methodologies to introduce the use of the fracture toughness into the industry it comprise or require the different activities that we are performing in this ToughSteel project. For example, the collection, organization, and analysis of the fracture toughness data measurements for previous and ongoing research projects to create a database of fracture toughness of advanced high-strength steel. This database is easily available now in the website of the project. And also, we are developing an industrial user guideline to describe the methodologies of the fracture toughness evaluations in sheet metals. And we are organizing also problem-solving workshops. The idea in these workshops is to enroll from 3 to 5 industrial companies has case studies to show how fracture toughness can be used to understand and solve crack-related problems. Also, we are organizing training workshops, as this workshop, for example, and webinar to introduce this essential work of fracture methodology and to receive feedback and facilitate an open discussion. And also, to facilitate the use of this fracture toughness of these developed solutions by the market, we are performing also standardization activities. The implementation of these methodologies to measure the fracture toughness in the industry will contribute to improve the material selection in cold sheet metal forming and also improve the optimization of the advanced high-strength steels microstructures. Also, the introduction of this fracture toughness will have to improve the prediction of the part performance to reduce the production losses during the sheet metal forming processes. And also, the methodologies will help to evaluate the crash worthiness of advanced high-strength steels for structural components and improve also the accuracy of the model process manufacturing and part performance to reduce the time to market. This information is available in our ToughSteel website that you are very welcome to visit. It's in 6 languages: English, French, Spanish, German, Italian, and Swedish. In the website, you will find general project information, the news and events, open access fracture toughness database that is available from today, the user guideline that will be available in the next days, scientific publication, and also public deliverables. And finally, also you can connect with us through the LinkedIn channel. Thanks, that's all from my side in this first brief introduction. Now let's move on to the next speech. The next speech is fracture toughness to predict edge cracking resistance and will be given by David Frometa. He is a PhD in material science and engineering, responsible of the materials mechanical behavior of metallic and ceramic materials unit of EURECAD. He has experience in sheet metal forming and fracture characterization of advanced high-strength steels and aluminum alloys sheets. So please, David, go ahead.
Thank you, Begoña, for your kind introduction. First, well, let me share my screen, my presentation. I guess you can see it correctly. Yes? Okay.
Yes, we can say.
Yes, yes.
Okay, thank you. Then, well, as Begoña said, the title of this presentation is Fracture Toughness to Predict Edge Cracking Resistance. As the title of the presentation implies, I will talk a little bit about how fracture toughness measurements can be useful, no, to understand or to predict this edge formability of high-strength metal sheets. This is the outline of the presentation. I divided this one in three main sections. First, a short introduction, introducing the new concepts of formability when talking about high strength metal sheets or high performance metal sheets. Then the second section is more focused on formability, also in the evaluation, experimental evaluation of edge formability, how to evaluate this edge cracking sensitivity and the influencing parameters. And finally, the relationship between edge formability and fracture toughness. Let's start by the introduction. As you probably all of you know, this lightweighting has become one of the main targets for many industrial sectors, for like the automotive, the transport, aeronautics, etc. Is in this context where this high strength or high performance sheet materials play a key role, in the development of lighter and safer structures. Owing to the high strength, these high strength materials allow to reduce the thickness of structural components, which the consequent important weight savings, while keeping or maintaining or even improving the safety of the structural performance. No? So they represent a great advantage compared to traditional materials. However, it's also well known that these new high-strength materials also bring new challenges, related to very limited formability, so higher cracking susceptibility, or the more frequent cases of cracking during cold forming or crash. One of the main concerns to sheet metal manufacturers and automotive stampers and also people of the sheet metal community when talking about this or when using this kind of high strength metal sheets is the problem of edge cracking or the occurrence of cracks or premature cracks during cold forming, rising from shared edges, from punched holes, etc., where the material is previously damaged. Main characteristic of this kind of fracture, of this kind of cracking, is that they usually occur far below the strain limits defined by traditional formability approaches, like the forming limit curve, also from the ductility levels obtained from tensile properties based on elongation, etc. So it is obvious that we need new fracture criteria for predict this kind of fracture, for this edge fracture behavior of these high strength materials. Then this brings to the table new concepts or new definitions of formability, and has raised this differentiation between global and local formability. Like, for example, in the case of advanced high-strength steels, where this global formability refers to the traditional definition of formability, which is the resistance against necking instability. It is represented by um, global formability modes, deep drawing, stretching, bending, etc. And this kind of formability is well represented by these traditional approaches, traditional formability criteria like the forming limit curve, also different tensile parameters like the elongation values, uniform or total, the strain hardening exponent, also a good indicator of the global formability. However, in these high strength metal sheets, we also have to take into account their local formability. This local formability is more related to the fracture resistance of the material itself. Some examples of local formability issues are this edge formability, for example, is one of the most important examples of local formability. Those also also the formation modes like the bending on tight radius or the crash folding behavior of high-strength metal sheets, which is also governed by this bendability, but also the damage tolerance, or the crack propagation resistance after the damage has initiated. And to measure this local formability, this traditional approaches are no longer suitable to predict this kind of fracture. So alternative parameters have been recently proposed, no, like the true fracture strain, or the set value, or the true thickness strain, which are parameters measured from the reduction of area or the thickness from the fracture surface of uniaxial tensile specimens. Also, the bending angle, which is measured from from the bending test according to the BDA 238. These are parameters that have been proposed to measure this local formability. But also, since I said from the, for by definition, this local formability is related to the fracture resistance of the material, we have also shown that this fracture toughness is a suitable property to predict or to understand this local formability of high-strength metal sheets. According to these different parameters, different alternative or enhanced formability mappings have been proposed recently. Like, for example, this is the Hans diagram where the true uniform strain is put as a measure of the global formability, and the true fracture strain here in the vertical axis is used as a measure of, of local formability. Then, according to the position of the steel grade in this diagram, we can define different levels of global and local formability. Also, alternatively, in a similar way, we recently proposed this classification diagram where we can use this uniform elongation as a measure of global formability and to understand this formability of the drawing, etc. And also, we can plot here the essential work of fracture or the fracture toughness as a measure of the cracking resistance or the damage tolerance of the material. So according also to this diagram, in a similar way, we can define different levels of global formability and cracking resistance. Okay, now let's focus a little bit on this edge formability. How can we experimentally evaluate this edge formability, and why it is a complex property to measure. Okay, first, well, maybe this is the most extended or the most well-known methodology to evaluate the formability of metal sheets, which are the whole expansion test according to ISO 16630. Here are some images of the experimental setup. The experimental procedure consists is a quite simple test. You have to prepare a hole in a square sample by means of a punching process. In this case, the ISO defines the cutting clearance or the punch to die clearance to be used for this kind of test, which is at 12%. Then after preparing this hole, then this hole is expanded by means of in a second step by a conical punch, like you can see here in the schematic view, until a first through thickness crack appears in the edge, or near in the edge of the hole. So the parameter that we measure here is the hole expansion ratio, which is measured from the relationship between the diameter at where this first crack appears and the original diameter. In this case, also the ISO defines an initial hole diameter of 10 millimeters, so the hole expansion rate is calculated from this relationship between the maximum expansion that we can obtain in the test and the original diameter. Okay, this is a quite simple test and it is well extended. However, the reliability of this whole expansion ratio value is often put into question, no? Because it depends on many variables. It depends on the whole preparation method, of course, also on in the system used for crack initiation detection. It also depends on the operator, also large variability, large scattering has been observed between different laboratories. So it can be very useful for first material screening. However, the reliability of the method is questionable. Also, furthermore, the experimental setup, this expansion also makes difficult to use different optical measure systems, like for example, a digital image correlation to evaluate fracture strains near the edge. So, according to this, different alternative, standard, non-standard, but alternative experimental procedures have been proposed recently. One of them are these hole tension tests, which in this case is quite similar to the previous one. In this case, we use a rectangular specimen. Then we prepared a hole by punching with the defined punch to die clearance, the one that we want to investigate. And afterwards, this sample is put in tension up to fracture, and by means of a digital image correlation equipment, what we can measure is here this we can I mean, of this full field strain analysis, we can determine these fracture strains near the edge. No, this also these parameters that can be very useful, for example, to implement in modeling afterwards. Alternative tests also like for example, the half specimen test. In this case, the experimental setup is a little different. Here we have a rectangular sample where that is cut. We have a transverse cut here. So this is well after the cut, this cut specimens is put into a die and is stretched by means of a hemispherical punch. Like this is this is the schematical view represents how to perform this test. This is a hemispherical punch or Anakajima punch, which is similar to one of actually is the same that they use for formability or for forming limit curve determination metal. And here, well, in a similar way to the hole tension test by means of the digital image correlation, we can observe the strain localization near the edge and determine also this strain limits near the edge. No? The main difference between both experimental setups is in this case this presents a stretching of an open cut, no, or a straight cut, while here we have a closed cut, which is a punched hole. Well, also alternatively, also there's also additional tests, like for example, the sheared edge tensile test, similar experimental configuration where we can use these digital image correlation equipments to define these edge fracture limits. However, as I mentioned before, this edge formability of the material is a complex measure. It's a complex property to measure because it does not only depend on the material itself, but also depend on different external aspects. Like for example, it's well known that this edge formability is greatly affected by the edge quality, which in turn is affected by different cutting or punching parameters like the cutting clearance, the tool wear condition. For example, we can see here how the fact of having a new or a worn punch can strongly affect the morphology of the fracture surface or and consequently the edge quality. Also, an important parameter to have into account when preparing or when cutting or shearing or punching, etc., is the cutting clearance, which is we can see here, depending on the cutting clearance, again, so strongly affects the morphology, the distribution of the different zones, which are divided to these 5 different zones of the edge, which is rollover, the bright zone, or the fracture zone, okay, and finally the work. Then, well, of course, this is no, one of the let's say the motivations that make difficult, no, to evaluate in a reliable way, let's say the edge formability of high strength materials. But also, when looking at the materials parameters, at the material parameters that govern this edge formability, we have to better understand what happens in this edge during punching or during shearing. For example, this is a gold standard part with showed some edge cracking, and we analyzed by means of a scanning electron microscope this edge, near this fracture edge. What we can see here is these images near this is the fracture edge, and this is the original sheared edge. What we can see is all over this the sheared edge. There's a lot. Oh, sorry. There's a lot of macro cracks in this case, but also defects, surface irregularities that also these defects can act as crack initiation sites. That these cracks tend to propagate during the subsequent forming operations like stretching or hole expansion, etc. Then it is important to keep in mind this that we are forming say an area of the material which is not deformed, is damaged, but it's more important is fractured. So we need to understand what is the material properties that define this this behavior, no? Which define the damage tolerance or the ability of the material to resist this damage or this crack initiation and propagation, no? Which in turn we know that is the fracture toughness. Now let's see how this fracture toughness experimentally correlates or how it's related to this edge formability. Well, maybe you have probably seen this graph, and so we always put it as an example, no, the correlation between fracture toughness and asset fungibility. You have seen in previous webinars on some of our publications. What we can see here is the relationship between the fracture toughness, measured in this case by means of the essential Walker fracture, and the Hall expansion ratio, which, as I said before, it's a well-established parameter to define this edge cracking sensitivity or edge formability of high-strength metal sheets. This is a clear example, no, of the clear relationship between fracture toughness and edge cracking resistance. So what we can see is that materials with higher fracture toughness tend to have this higher edge cracking sensitivity. Lower edge cracking sensitivity, higher edge cracking resistance. So, well, this is, as I said, this Hall expansion radius is well established. However, since it's not say the most reliable parameter, so different researchers have put a lot of effort in identifying material properties that could help to better understand in a more objective way this damage tolerance of the material or this edge formability. And that's where we bet, we strongly think that this fracture toughness is one of the most suited parameters to understand this fracture behavior. That's the case for the Hall expansion ratio, but also with different experimental setups, we have observed different similar trends. In this case, these are values of results from Hall tension test. Here, the bars represent values of fracture strengths measured at the whole edge. Okay, so this is fracture strengths or edge fracture strengths. What we can see a similar trend that the steels with lower fracture strengths again show also lower fracture toughness as measured by the essential Walker fracture here indicated by these blue points. You can see on the other hand, materials with higher fracture toughness show higher also higher fracture strengths. But also it's interesting to note here, while for example in the steels having low fracture toughness, how we can see, for example, a clear trend indicating a clear decrease of the edge formability when increasing the cutting clearance, for example, from 10 to 20, in this case of dual phase 1 and dual phase 2. However, when we move or we take a look to steels or tougher steels with greater fracture toughness, this trend is not so clear. So it's evident that this edge quality is important, but so the tougher the material, the higher the fracture toughness, the more able is the material to resist the different damage induced during shearing or punching. Now, what is the say the physical relationship that displays the similarities in the similar trend between fracture toughness and edge fracture? Well, it is reported in the literature that the fracture mechanisms governing or occurring during both fracture mechanics tests and also edge fracture are pretty similar. Also, we have seen in the previous slide, from the images from scanning electron microscope, we have seen that this is cracking at the end is a nucleation or propagation of cracks. Actually, if we take a closer look to the fracture surface of a pre-cracked specimen, like the one that we use for fracture toughness testing. Here, this is the fracture surface of an specimen. On the fracture surface of a shared edge, of an edge fracture, okay, we can observe certain similarities between them. For example, here, the formation of this triangle zone or this flat zone at the beginning of the crack initiation and the transition to the more flat or sort of more slant fracture of 45 degrees. Also, if we look or if we measure the thinning ahead of these two experimental setups, what we found is that measuring this true thickness strain, which is measured by this thinning or by the reduction of thickness at the crack tip, when we compare the values these strain values in pre-crack the specimens for fracture toughness testing, and we measure different, so similarly, this thinning just near the edge crack in hole expansion test. What we found is that surprisingly or not, because coincidentally these fracture strains or this edge thinning were very similar for both of them. No, so this is further evidence that the fracture mechanisms that are occurring in both kind of fractures are pretty similar. But also this furthermore this definition of the thickness strain or this edge thinning can help to define objective parameters to define this edge thinning limit or this edge formability based on this edge thinning limit, which at the end also can be, for example, can be an objective failure criterion to be implemented in modeling, for example. No? But later in the next presentation, we will see a little bit more how to implement these fracture toughness testing approaches in modeling to predict edge cracking. And finally, well, to conclude my presentation, so a summary of the conclusions from this presentation, we have seen that these traditional formability criteria are not suitable to predict edge formability. We have seen also that there are different experimental methods for edge formability assessment, like the hole expansion ratio, hole tension test, or half specimen test of the shared edge tensile test. Importantly, a key or important message is edge formability depends not only depends on material itself, but also on the edge quality. And finally, we have seen that this fracture toughness, it is a useful material property to understand edge cracking sensitivity of high-strength metal sheets. And according to this experimental observations, we propose the alternative or new fracture criteria based on thickness strain or fracture strains measured in pre-crack specimens. And that's all from my side. Thank you very much for your attention. And if you have any question, I will be happy to answer at the end of the session today.
Thank you very much, David, for the presentation. Remember that you can type your questions in the chat box, and David will deal with them, as he's mentioned it at the end of this webinar during the open discussion session. Now let's move to the next talk. The next speaker is Michele Maria Tedesco. He's going to talk about the application of fracture toughness measurements in the industry, successful case studies. Michele is the global responsible for metals in Stellantis, with a broad experience in sheet metal forming. He's also coordinator of several projects, authored of numerous publications and patents, and he is an advisory board member of Automotive Circle. So please, Michele.
Thank you for the presentation, Begonia. Do you see correctly my screen?
Yes.
Okay, perfect. So, as is introduced before by David, during this presentation, we will see a couple of case study that we faced during the previous year. The first one is about the underseats beam, and the second about the aluminum reinforcement. Both these case study came from the automotive sector, and after that we'll go through with the conclusion. So about the first case study about the underseats beam, this kind of component are located in this area of the vehicle, are the highlighted red component, and usually this component has several objectives. The first one is to connect the underbody of the vehicle with the seats. They have also a function during the stiffness of the vehicle, so the torsional stiffness. They work also for the durability. And finally, but it's always important during the crash. For this target, they have to absorb the energy during the crash, and also to limit the intrusion during, for example, side pole impact, to prevent and to assure the safety of the occupants of the vehicle. So these two kind of components are very relevant for the safety of the people inside the car. Usually, these are made with dual phase 800 steel, where 800 is the minimum tensile strength of the material, and the matrix is ferrite and martensite. For lightweighting, the proposal is to use high strength steel to have the opportunity to reduce the thickness and so the weight of the car. Here you can see the mechanical properties, the comparison of the mechanical properties between the dual phase 800, dual phase 1000, and the complex phase 1000. In terms of ultimate tensile strength, the DP1000 and the CP1000 are comparable, while if we are looking for the elongation, we have a high difference between the DP800 and the rest of the material. During the projects, so the vehicle design was chosen the DP1000 because it has a higher elongation than CP1000 due to based on that, for sure, we will have higher global formability. But at the end, when we stamped the first component, we recognize an edge cracking from the border of the component. So to solve this issue, we tried to use the CP1000 grade, and also having less elongation, we were able to stamp the component without any crack. As you can see, the tensile strength, the tensile curve of both the material is slightly different because the dual phase has lower yield stress. So the yield is lower, is about 700 megapascal, while the yield stress of CP1000 is higher, and the big difference is also in the elongation that is much lower for the CP1000 than DP1000. But at the end, the property that we are interested in to solve this problem is not the elongation, but as I said before by David, is the essential work of fracture. Comparing the comparing the essential work of fracture of CP1000 and the DP1000, we can see a very big differences. The OK material, that is the complex phase, is much higher essential work of fracture energy than the DP1000. This means that this material, in this material, if we would like to propagate the crack, we need more energy. And so for this reason, during the stamping of this component using this material, we didn't found any crack, and we make the running change in production using this kind of material. So these give us an important lesson learned that we keep for the other vehicles. In the meantime, for the innovation, and also for to reduce the weight of the component and to assure more complex geometry, we studied together with Eurecat different material. This is the graph that showed before David, in which there is the correlation between the Hall expansion ratio and the work fracture, in which we can see there is a direct correlation between these two kind of measurements. For this reason, taking into account the experiment done in the different European projects, we put our attention on the material highlighted in red in this graph. Especially, we focalize our attention to trip magnetic material because is a good compromise between the Hall expansion and essential work of fracture value, and also formability, because you can see here there is the dual phase 1000 that we tried to use in previous vehicles, and here there is the CP1000 that we used to solve the problem that we had in production. Based on this information and comparing the mechanical properties of DP1000 and trip magnetic material, we found that these could be the good material to replace the current one that we had in mind, that was to return back to DP800. This material, the trip magnetic material, is able to combine high elongation comparable to the DP800 with a good properties of Hall expansion. On that, we tried to make successfully the exercise on Alfa Romeo, Giulia, and Stelvio using the trip magnetic material, and comparing the results to the baseline solution that was the dual phase 800, we were able to achieve a 19% of weight saving because we reduced the thickness from 1.6 to 1.3 millimeter for the frontal seats cross member, and a 14% of weight saving for the central cross beam, in which we reduce the thickness from 1.4 to 1.2 millimeters. In terms of performance, you can see here a simulation. The horizontal line, blue, and the red one are the target that we have not to exceed, while the curves, the blue one and the red one, are what we found in simulation and in the real crash. As you can see, the gap between the curves simulation and the real test and the target is much high, so we are high conservatives. So this means that could be in the future also the opportunity to decrease a little bit more the thickness if we take into account only the crash performance. So this is today our baseline for the new projects, and we achieve this target thanks to the Hall expansion and essential work of fracture methodologies, and also to, for sure, working together the steel supplier to develop together this grade. The second case study is about aluminium reinforcement, in which, as you can see in the picture, there is an edge crack problem during the forming. For that, we took in consideration two kind of different alloys, the not okay and the okay one. In terms of chemistry, The main differences is about the iron, silicon, and manganese content. That for the new alloy, the OK1 is lower than the previous used to realize this component. But in terms of grain size, we didn't found any differences between the two alloy. So looking at the microscope, they are completely similar. We go ahead with the investigation, taking into account the mechanical properties. In terms of yield, tensile, and elongation, the two alloy are completely comparable. We didn't found any big differences in these properties, and also considering the forming limit diagram, in blue is reported the not okay material, so the material that caused the failure, and in red the new material with the changed chemical composition. The FLD are different, but not so much. The new material has a slightly higher FLD curve, but this not can explain the different behavior during the forming of the component. So for this reason, we go deeper, analyzing the essential work of fracture of the two alloys, and here really we found the main difference between the two alloys, because the not okay, as you can see, has half of the essential work of fracture of the new chemical composition, as well as also for the plastic work during the essential work of fracture test. These different behavior could be justified in taking into account the second phase volume fracture inside the alloy, so the intermetallic compound inside the two alloys, because for the new chemical composition that allow us to stamp the component, the fraction, the second fraction is just 1.2%, while in the not okay is 4.4. So this means that in the previous alloy, the intermetallic layer, intermetallic compound is higher than this one, and could have a strong effect on the plastic work and in the essential work of fracture. So based on that, we can say that there is the possibility to determine in advance the edge cracking problem. The essential work of fracture could be used to select the right material in the right place, hoping in advance to have the first pieces stamped. And if we are able to consider the essential work of fracture during the simulation phase, these could allow us and the stampers to prevent to use the wrong material, and also to work to solve the stamping problem. Anytime that we are able to predict some failure on some problems before to milling the die, we can save money and time. And giving this last message, I would like to be connected to the next presentation that will be done by the colleague Riccardo. Anyway, I am available if you have a further question at the end of this section. It will be my pleasure to answer to your question.
Thank you very much, Michele. And also to the attendants, you can find the link of the project website, and also in the chat there is the link to the the fracture toughness database of the project. Okay. Next talk, it's about limitations of short edge formability simulations and will be given by Ole Sandin. He is PhD student in solid mechanics at Luleå University of Technology, and he is conducting research within numerical modeling of shear cutting in advanced high-strength steel. So Ole, you can start. You are mute.
There you go.
Yes.
Okay. Hello and welcome to my part of this webinar, where I will discuss limitations on shared edge formability simulations. As Begonia said, my name is Ole Sandin and I'm a PhD student at Luleå University of Technology at the Solid Mechanics Division. And my research is within numerical modeling of shear cutting. And I hope that in the end of this presentation, you will understand how this relates to fracture toughness. First, I will give you a short background on why am I discussing this topic today, where I will introduce you to the effects that cracks have on advanced high-strength steel designs. And after that, I will present a small published study on how cracks affect numerical modeling accuracy. And this will later lead us on to the topic of this presentation, that how cracks gives limitations on shear edge formability simulations and shear cutting simulations. And then to sum this up, I will state some conclusions and further work needed in this area. But first, to the background. And as stated in previous webinars of this project, we know that the high strength of advanced high strength steels, they enable downgaussing and weight saving, but you can keep or even improve the structural integrity of your part. But we also know that the high strength and fairly low ductility gives other challenges compared to softer mild steels. And a common topic is edge cracking. Seen during forming operations, and these cracks arise from the sheared edges as they are subjected to stretching, and they are, as David said, they're quite hard to foresee with conventional predictive tools. And another similar problem is cracks arising in crash components that affects, like in this case, the foldability of an automotive crash box. And furthermore, we have fatigue properties of high-strength steel that are continuously being investigated, and fatigue failure is obviously also linked with cracks. And what all these three cases have in common is that cracks and crack initiation and propagation have a huge influence on each component in each of these processes. And a common conception is that the shear cutting process that you find early in the production stages induces damage in terms of micro cracks. These cracks will later on affect all of the processes previously mentioned, because you will see that these cracks will grow during forming of the sheared edges, and they can turn into edge cracks. And during crash, we have extreme deformations. These micro cracks are likely to be stretched and to be propagated. And in worst case, this can impair the performance of your crash absorbing part. And fatigue cracks can, of course, also grow from the micro cracks and become an initiation for fatigue failure. So consequently, one can conclude that cracks define important aspects of high-strength steel behavior, and it is of great importance to control and predict the influence of cracks in the product development process. And unfortunately, cracks will more or less always exist in some way in advanced high-strength steel designs, but knowing how to relate to them in a numerical modeling early in the product development process can aid in avoid late design changes and material changes or costly tool redesigning. And next, I will present a study on what cracks can do to your numerical modeling results. And this study was done in the Cutting Edge 4.0 project as a part of a work package with the purpose to define constitutive modeling for failure and damage models to be used in shear cutting simulations. And in this project, the phenomenological failure and damage model was calibrated and evaluated with regards to being used in a digital twin of a shear cutting process. And one important aspect of this evaluation was to investigate how well this phenomenological model dealt with cracks in materials. And in this study, two high-strength steel grades with similar strength but slightly different ductility was investigated. And the effects from cracks were investigated through numerical modeling of double-edged not tensile specimens or dent specimens. And we used one set of dent specimens with fatigue cracks grown from the notch ends, and one set of specimens without the fatigue cracks. And these specimens you only called notched specimens. Then we performed numerical modeling of this test, and they were validated and correlated against the corresponding experimental results. And we did this for a large number of ligaments lengths, ranging from 6 to 14 millimeter. And the dent modeling was done using the phenomenological failure and damage model Gizmo, which is implemented in the finite element software Elestina. And the fatigue crack was modeled using duplicate nodes along the crack tip, and we used solid elements for this particular modeling. And this testing procedure was used due to its simplicity, because it gives you a pure mode 1 crack tip opening, and you can avoid uncertain parameters such as friction and dynamics and joints or etc. that otherwise in your modeling probably will be based on assumption that might cause deviation in your numerical modeling. And in order to use a Gizmo model, it needs to be calibrated for your intended materials. And for you who are not familiar with Gizmo, so it's a stress-dependent damage and failure model in Elestina. It is developed for ductile damage and failure. And Gizmo can use an arbitrary failure strain as a function of stress state, stress traxiality. And if you want to also deload the angle parameter to define failure in your material. And combined with ductile damage parameters, it can, with good accuracy, determine ductile failure and damage in, well, for instance, high-strength steel or aluminium. The Gizmo models were calibrated to later be used in a shear cutting model, so it needed to have failure data for a wide range of stress states. And we used tensile testing for different tensile specimens, which gave us a failure strain for a large range of stress states. And the tensile testing data was used to calibrate a modified Moore-Coulomb failure surface, which defines failure strain as a function of stress axiality and load angle parameter. And this means that you can get failure data to be input in your Gizmo model that spans everything from like plane strain compression, uniaxial compression, shear, uniaxial tension, and plane strain tension, and biaxial tension. And everything in between. So to see that the Gizmo models were accurately calibrated, they were validated against both bending experiments and against the tensile testing experiments that was used for defining the modified Moore-Coulomb fracture surface. And the bending experiment consisted of a sample plate on top of frictionless rollers and a bending punch that will, consequently just bend the plate. And the experiment will finish when you get a 10 Newton force drop after peak load. You then examine the sample for cracks and see if you have cracks in the same place and for the same load and displacement as in your modeling. And the tensile testing is quite straightforward. You in experiment and in modeling, you just pull the specimens until it breaks, and then you compare failure initiation site and force displacement curves. And in all these experiments, the specimens were prepared such that the edge damage and microcracks are avoided. So we can consider these specimens as undamaged specimens. And here I only show the data for the CP1000 HD material, and in order to not crowd the slide, but as you see, the correlation is good for both bending and tensile testing, which means that, well, the Gizmo model works very well for the shown load cases and stress states and for undamaged material. But so to the dent modeling. Here you see the graphs to the right. On the upper row, we see the force displacement results for notched, that is undamaged dent specimens. And we see the entire range of ligament lengths. And we see that the correlation is good, at least until the end of the tensile testing, where you have a lot of material failure and fracture evolution. But on the lower row, for the cracked specimen, we see a quite poor correlation. We see that the numerical results they drop later than in experiments, which means that the fatigue crack grows and propagates earlier in experiments than in modeling. And it's apparent that the modeling really cannot capture the crack initiation in the fatigue crack tip, why we have over-predicted force displacement results in modeling. And the observation from this is that if you try to model processes involving cracks and crack propagation in high-strength steel with a Gizmo-like model, you might run into a problem. And in this case, it seems like you need a different approach to deal with the crack tip stress and crack tip failure and the propagation. And the failure locus that we calibrated, it doesn't really include this stress state. And I guess you can see how this can be an issue. So if you imagine having a form simulation using this Gizmo model, and where you have an edge that is being stretched. And if this edge in real life have a crack, I'm quite sure that you will have quite bad correlation in your model with reality. And next we'll see another case of numerical modeling where this inaccuracy can give and has given me quite some problems. So we will move into kind of the topic of this presentation. So we look into shear cutting and how cracks can limit the accuracy of such simulations. And for you who are not familiar with shear cutting and the shear cutting process, we can quickly look into the main steps of the process. Initially, we have a blank and a workpiece, which will be cut. And then we have a die and a punch, where the punch will move downwards and remove the right side of the blank. And at first, we get kind of severe plastic deformation and a rollover formation in the early part of the shear cutting process. Then we get penetration of the blank, where shear failure occurs at the edge of the punch. After some shear failure, cracks starts to initiate and starts to grow from the punch edges and die edges. And this crack propagation is fast, and you will get a sudden fracture, and your shear cutting process is finished. As mentioned before, this process induces damage to the cut edge of the blank, and this will affect the formability of your part. So in a numerical model, in numerical modeling, if you can simulate this process, the shear cutting process, and predict the cut edge damage, you should be able to control or at least estimate the formability of the final part. But to be able to numerically model shear cutting, this puts high demands on your material models and your damage and failure models. And here you can see the shear cutting process and the cut edges in separate stages along the process. These images are from interrupted punching tests conducted by Eurocat, where the shear cutting process was paused at a number of stages along the process, and the cut edges were examined. And because here you see the rollover part of the process, and here you find the large deformations with severe plastic strains. And in modeling, you also see very high element distortions in this process. Here it is crucial that you can model high ranges of plastic deformation. But if you look back at the experiments and the modeling a few slides back, this seems to be possible with the Gizmo model. I mean, we could model severe bending, notched specimens, and notched dent specimens well into plastic deformations with good accuracy. Then we have the material failure. So when the rollover is finished, we have a failure in mixed compressive shear stress. Then we have pure shear material failure. And then in the end of the shearing process, we have kind of a mixed tensile shear failure. And also looking back on our previous results, this also seems possible to do with the Gizmo model. If you remember that we could model failure for a lot of different stress states in our tensile testing. However, when we look at the end of the shear cutting process, we realize that we can move into some problems, because here we see the cracks that are started to growing from the punch edge and the die edge. And looking at the cracked dent modeling, one can assume that the Gizmo model won't be very accurate in capturing this behavior. And as we thought, the numerical shear cutting modeling have inaccurate crack initiation. Here you see in the red a finite element mesh of a cut edge next to experimental cross section of a cut edge for the same tool clearance. We see that the rollover seems fine, which means that we have okay plasticity and our compressive shear failure modeling is on point. But the shear zone is too long in finite element model, which means that the crack initiation after the shearing is inaccurate. And in the end, this gives an inaccurate cut edge shape with wrong fracture angle and in a whole inaccurate cut edge damage assessment. And this is a clear example that without treating cracks in a proper way in modeling, you might end up with not so good results. So to sum this up, I will state some conclusions from this presentation and thoughts about future work. And I think that I made my point at least. If you model processes involving cracks and crack propagation, you need to take them into special consideration. The strain-driven ductile damage modeling presented today is most likely insufficient for this. And if cracks are not considered, there's an imminent risk that your modeling accuracy will diverge as cracks appear to affect the advanced high-strength steel behavior. And today you find several numerical methods that are specialized on crack tip modeling. There are various ways of constructing your mesh in order to model crack tip plasticity, and you have XFEN that are shown efficient in modeling of crack propagation, and you also have other meshless methods such as peridynamics that are suitable for this. However, few of these lack the versatility and the user friendliness of the Gizmo model, which is a problem when you modeling, for instance, shear cutting. We have damage model that needs to be handled a large range of failure modes and failure triaxialities. And as my research is within numerical modeling of shear cutting, I obviously need to address modeling of cracks. The work done within ToughSteel is therefore great interest to me, as one possible way to approach material failure in modeling maybe can be to consider the fracture toughness in model instead of the failure strain. And I will therefore follow the communication in the ToughSteel project with great interest and looking forward to learn more about fracture toughness and hopefully find ways to apply fracture toughness in my modeling. So, well, that was all for me. Thank you for listening.
Well, thank you very much, Ole, for your interesting presentation. I'm sorry for the change of moderator just in the last time, but I think it seems that Begoña is having some technical problems with the internet, so I'll take the charge from now on. Now is when it's time to move to the last presentation of today, which will be done by Ricardo Hernandez. Ricardo is a researcher in Eurecat. He's a mechanical engineer and has a master in material science and engineering. He has been working as a researcher in Eurecat since 2004 with a wide experience in simulation, mainly on metal plasticity and forming analysis. And he will present today a presentation titled Application of the Essential Work of Fracture in Sheet Metal Forming Simulation. So please, Ricardo, it's over to you.
Okay, David, thank you again for your kind introduction. And in my presentation, I will show one way to use the toughness obtained by the essential work of fracture in the finite element analysis. The idea is include the capability for analyze the edge cracking along all the three edges when we stamp a steel part. Next one, David, please. Okay. I will start with a very short introduction, and I will explain how is our model and how we calibrate it for define the material chart in the simulation. And finally, I will present some examples where you can see the application of our model in a real cases. Next one, please. Always the same, but as it was very well explained in the previous presentation, the automotive industry continues research for lightweighting and safety, and new steel are needed to achieve this high formability, the high strength, the high toughness, and the last generation of this the advanced high strength steel is one of these solutions. For the car engineering, the conventional material characterization and the conventional material modeling, in many cases, is not enough for this new steels behavior. And new approach, mainly for the failure criterion to improve the forming and the crash simulation, is needed. And in this sense, we are looking for more easy testing for models to enlarge the analysis to more failure conditions, and for example, to complement the FLD, the formability limit diagrams, and all toward to improve both the forming simulation and also the crashes analysis. Next one. Okay, for the edge cracking analysis, we were working with a ductile damage model implemented in the finite element commercial software Abacus. We can define when and how is the element degradation, and defining a damage load that makes the element lose its stiffness. For it, we need to define the damage initiation criterion and a damage evolution law defined by the parameter D. This is the most important parameter. It's a function that defines how is this damage evolution. The damage initiation is the equivalent plastic strength as function of the triaxiality when the element starts to lose the stiffness. And the damage evolution defines how grow the damage as function of the element plastic displacement, not the plastic strength. This is an important thing. And we use the plastic displacement in the element to avoid problem with the element size in the mesh. Normally, linear or exponential laws are used, but now we propose to use a power law that grow fast in the last part of the plastic displacement. For calibrate the model, we obtain the parameters by the toughness measurement, by the essential work of fracture methodology, You can remember all the explanation from the previous presentation, and it is through the double edge notch tension or the DEN specimens. It is a tensile test with 2 notches where we have a specimen with different ligament lengths between these notches and with different ligament length and with different specimens, we obtain a measurement of the toughness. And a difference that Ole presented previously, we calibrate the model with the specimen with cracks in the notches. Next one, please, David. To obtain the model parameters, we use a reverse engineering process where we simulate the DEN test and through an optimization process, we change the model values up to obtain a good fit between the simulation and the results. The simulation model is a quarter of the specimen. We use shell elements, and in the ligament area, we use a 1 millimeter element length. This is also important because the calibration is for the 1 millimeter element length. We have a big element in the crack tip, but in this big element, we have all the behavior of the crack. And this is a full empirical approach, but in our last investigation, we are observing that the values of the failure model are quite similar to the thickness strain at the crack tip, and we are working to propose a physical sense for our model. Like presented previously by David, we have a measurement of the thickness in the cracks for the test and also for the hole expansion or for cracks in the real component, and is very similar to this measurement with the values in the damage evolution model. Next one, please. Now I can show the real cases that we use for the model validation. And here you can see the hull specimen dome test. In this case, you can see how with our model, with the essential work of fracture, we can catch the fractures in the edges. And when we use only the FLD, we can see this type of failure, and we can see any cracks in the edges. The next one, please. We can also use the model to analyze the hole expansion operation. But we have the limitation of the mesh size because I explained that we use a 1 millimeter element length, and in some cases this 1 millimeter length are too big for small holes to mesh the holes when they are small. In this case, for example, we show a hole of 10 millimeters of diameter, and also we can see again how the models show the failure. And when we use only the FLD, we don't have failure in the hole. The next one. The more interesting example are the real component. And this is a T-node geometry proposed by Fiat to check the behavior of their materials. Is similar to the top and bottom areas of the B-pillar component. And again, you can see the difference of incorporate the essential work of fracture failure and using the essential work of fracture, we have this edge cracking, but when we use the FLC, the crack is in the middle of the component and don't start in the edges. Next one. Here again, using the same tooling in different configuration, changing the black dimension, and we obtain also the similar results. It's important remember that we use our model in conjunction with FLC, our model for the edge cracking, FLC for what happened in the bulk material, and we use the essential work of fracture only in the edges. With this model, we have a good tool for the material selection. And in this case, we analyzed these three materials, the CP and DP. The next one. This is other one of the real component from Fiat. And again, you can see the difference between use only the FLD and use the FLD together with our essential work of fracture criterion along the edges. With the FLD, the crack is very big in the middle of the component. And when we have the essential work of fracture, the crack starts in the edges and the failure is very different. The next one, please, David. The model also can be used for the crash analysis. In this case, I showed the study of crack propagation in notched beam using a crash testing. In the four displacement plot, in the black line is the experimental results. The red one is the simulation with our model. And the blue line, the dotted one, is the simulation using only the FLC. And you can see that with the FLC, we have an overestimation of the energy in the crash test. And the model works well when the crack starts at the edges, of course. And also we are working in the evaluation of the strain rate sensitivity, but in the analysis, in many analyses, the characterization through the slow rate is enough to analyze the failure in this crack condition. But in crash simulation, we need care to use the model because in some cases the strain rate is necessary to achieve a good results. Okay, finally, in conclusion, it's a new approach to define the ductile damage model based on an essential work of fracture by dent test is presented, showing a good edge cracking prediction on the forming operation of the new advancing high stress steel. It can be used in conjunction with the FLC to analyze the forming processes, and we can also use, for example, for hole expansion with the limitation of diameters. The model follow an empirical methodology and required an inverse engineering integration process to define the material chart. This is the problem now is we are looking for a directly definition from the test, looking, for example, this thickness strain, and only with this value try to obtain the full parameters of the model. And also thinking about the approach, the failure characterization was adapted to a square shell element with 1 millimeter element length, and we think that this type of mesh can be used easily on complex parts of simulations. And this is all for my part. Thank you for the attention. And if you have a question, this is the time. This is the last presentation.
Thank you very much, Ricardo, for your presentation. Now let's move. Well, sorry, I got cut off. We're having some internet problems in the office, but I hope it's going well now. Okay, let's move to the open discussion. Let me check the chat. I think that we don't have any question in the chat, but you can raise your hand if you have. I have some questions, but I will if the audience have some questions. No? Please take advantage that you have the experts here and they know a lot about this subject. Okay, we'll start with one question to David. Okay, well, there is a first question from Valerio Sipo. And he says that thanks for the report, Dr. Oli. Regarding the shear stress that causes microfractures, it's possible that during the industrial production of a flat laminate with reducing the width, trimming with continuously rotating knives can cause the same effect on low carbon steels?
Wow, that's a good question. Trimming with continuously rotating knives. I'm not very familiar with that process type.
Please, Valerio, you can speak more if you want.
Yeah, please.
If you want to
elaborate.
talk, maybe, yeah. Valeria, are you there?
Hello?
I don't know if they. Okay.
It's muted, Marina.
Thank you.
Okay.
No. We product flat limit steels, and during the reducing the width of the coil, we using rotating knife on the edge of the coil.
Mm-hmm.
So we are some problem with our customer that causes fracture on the edge when they close the laminate and welding the edges.
Mm-hmm.
So near the welding, there are some fracture, and we don't know how is it possible because the chemistry of steel is correct and the heating process are correct too. So I am asking myself if the rotating knife can cause the same effect that you report before.
Yeah, well, yes. I don't really know, but probably because you see during shear cutting that you can get not only micro cracks, you can also get pretty large geometrical deformations in terms of, well, the rollover that I show you, so severe plastic deformations, but you can always also get the burr, which is kind of a part David showed you, quite large geometrical defect that goes out of the plane, and maybe that could have an effect in this process. Not really sure, but possibly. I mean, it's a huge deformation to a material to be subjected to shear cutting, and I don't know if low carbon steels are milder. Maybe they can have even larger defects than we see in advanced high strength steel.
Okay, thank you. Because the crack on the edge are very, very similar.
Okay. Interesting.
Thank you.
If I have, I think that this could be a good case study for the next activity of this project, so the open call. If you like, Valerio, you can submit this case for the open call, and we can analyze the material. We make the metallurgical analysis, the essential work of fractal analysis to find a correlation within your problem and the essential work of fracture to determine the difference between the okay and not okay material, if you agree.
This is very interesting. Possible. I must ask permission to do. but it's a really great opportunity. Thank you.
Yeah. Please consider that it's something for free. It's not request any payment. We will select 3 or 5 cases and we will make this investigation. So it's a great opportunity.
Thank you very much.
Yes, you will find information in the website. If not, you can write or send a message to us. Okay. Well, if there are no more questions, or I have one to David. David, what is the difference between using the whole expansion ratio or the essential walk of fracture? I mean, if you have to design a part with an advanced high strength steel, you can to select the material, you can use just essential walk of fracture.
Well, thank you, Begoña, for the question. I think, well, that's a frequently asked question, no? And we talk because most of the people know the whole expansion ratio, which actually is a standard. So when you start working on the whole expansion ratio, the more you work on, the less you like it, because this large variability, and it depends on a lot of different variables, as I said during the presentation. Of course, it is useful to first, let's say, to do first screening of materials. But as I said, also this edge formability measured by the whole expansion rate is greatly affected by different factors, and by like the edge quality or the system that they use for crack inspection, or a lot of variables. Then the difference with essential walk of fracture, the fracture toughness, or other parameters is that this is a material property, that it doesn't depend on the geometry, or doesn't depend on the crack length, and so on. So if you want to better understand what is the material property of the material itself, the material damage tolerance, it is better to use material properties that define this crack propagation resistance. Also, because we have seen also here that this essential walk of fracture is a parameter to predict this edge formability, but we have also seen that it's very suitable to predict other kind of cracking related phenomena, like the one of, like Ole presented, also like this presence of cracking during severe deformation, like in the case of crash tests, or something similar. So, but the main difference is that that this essential walk of fracture is a material property. It depends on the thickness, because thin sheets in plane stress, it depends on the material thickness, but it is a material constant for that sheet investigated.
Okay, thank you. I don't know if there are more questions now from the audience. No, I don't see any question. I have questions to Michele. Michele, considering these case studies that you have shown, and the importance of this essential walk of fracture values, do you think that this information we've easily integrated in metal sheet standards, or?
Thank you, Bego. Yeah, I think yes, it's just something relating to the time, because in the past we only have the chemistry and the classical mechanical properties. After that, with the complex geometries and the more advanced high strength material, we start to include the all expansion ratio inside to the metals specification for some particular materials. And I think that as soon as we will consolidate this experience with the essential walk of fracture, we could and we will integrate this information in our specification.
Okay.
So,
Thank you.
Sorry, if I may add something here also regarding the standardization. Well, as you know, also in collaboration with CRF and other industrial partners in the previous project, which was the Form Planet, which also we elaborated this THEN workshop agreement, or this CWA, which is, well, it already said, is it available on the THEN workshop website. It's like a testing, it's like the first step towards the standardization of the method, and it's like when it is a workshop agreement. Actually, it is a reference document with we describe the methodology, how to apply the method, the recommendations about the specimen geometry, the notch preparation method, etc.
Okay, great. If there are no more questions, I have also one question to Ricardo. Ricardo, please, are you there? Yeah.
Yes, I am here. Open the camera.
This failure criterion that you propose can replace the Fermi limit curve. What do you think?
No. I explained that the model needs work together with the FLC. The FLC work well in the bulk material in the middle of the sheet, but don't catch the edge cracking. For this, we propose this model to use in the edges to catch this problem of edge cracking.
Because if I understand well, that the edge cracking is a more local problem,
Yes.
no? And the formability, the global formability is about all the global field, but it's not.
This is, yes.
Okay, so interesting. There are more questions or comments? Okay, if not, I would like to invite you, please, Marina, can you share the slide with the invitation from the next event? The upcoming event will be held in Stockholm the next 7th of June. It's an industrial workshop in this case about industrial application of the fracture toughness, characterization and modeling approaches with the following topics: measurement of mechanical properties for sheet metals after large deformations and high strain rates, investigating crash characteristics of advanced high-strength steel components, perspective from the industry, and numerical modeling of shear cutting in high-strength sheets. You are very welcome to this industrial workshop. You can register by yourself in our website. You have the information and the link here in the chat. Let's finish the meeting. Thank you all for attending, and I hope to see you soon. See you in the next event, and thank you very much also to the speakers and for your time. Thank you very much. Bye-bye.
Thank you. Goodbye.
Bye.
Thank you, everyone.
Bye-bye.
Bye.